When we ask, how big is the Andromeda Galaxy, we're not just looking for a number, we're stepping into a question that challenges our sense of scale and understanding of the universe itself. Measuring Andromeda's size means grasping distances so immense that even light, traveling at 300,000 kilometers per second, takes millions of years to cross them. This question isn't about simple dimensions, it's about perspective. About how something so vast can exist just beyond our sight, yet shape our understanding of the cosmos itself. The Andromeda Galaxy is a window into the grand architecture of the universe, reminding us how small we are and how boundless space truly is. So, watch this video till the end and subscribe to the channel. Let's start. As we step deeper into our cosmic journey, we move from the question itself to the subject at the heart of it, the magnificent Andromeda Galaxy. To understand its size, we first have to understand what it is. The Andromeda Galaxy, known officially as Messier 31 or simply M31, is one of the most striking and studied objects in the night sky. It's a spiral galaxy, much like our own Milky Way, a colossal collection of stars, planets, gas and dust, bound together by gravity, arranged in sweeping, graceful arms that wind around a bright central core. When astronomers describe Andromeda as a spiral galaxy, they're referring to its structure. A flattened, rotating disk filled with billions of stars, glowing nebulae, and dark ribbons of interstellar dust that trace the spiral arms like the strokes of a cosmic artist. These arms swirl outward from the central bulge, where a dense cluster of older stars and, at its very center, a supermassive black hole reside. In photographs captured by space telescopes, Andromeda's spiral arms glow with the light of countless young blue stars, the sign of active star formation, while reddish clouds of hydrogen mark regions where new stars are being born even now. What makes Andromeda especially fascinating is not only its structure, but its proximity. At roughly 2.5 million light-years away, it's the closest large galaxy to the Milky Way. While the universe is filled with smaller galaxies orbiting ours, Andromeda stands out as the nearest spiral galaxy comparable in size and shape to our own, a kind of mirror, showing us what our galaxy might look like if we could step outside it and gaze back. Astronomers have long captivated Andromeda because it's so near on a cosmic scale that we can study it in remarkable detail. Under a dark, moonless sky, far from the wash of city lights, Andromeda can actually be seen with the naked eye, appearing not as a pinprick like a star, but as a faint, fuzzy smudge of light. What's truly mind-bending, though, is that when you see that dim glow, you're looking at light that has been traveling through space for 2.5 million years. The photons striking your eyes tonight began their journey long before modern humans even existed. The fact that Andromeda is visible without a telescope has made it a familiar sight to observers for centuries. Ancient astronomers didn't know what it was. They saw it as a mysterious cloud-like patch in the constellation Andromeda, named after the mythical princess of the same name. That's where the galaxy got its name. It wasn't until the advent of modern telescopes and later photographic technology that astronomers began to uncover its true nature. Not a small cloud within our galaxy, but an entire galaxy in its own right, an island universe millions of light-years away. Andromeda's beauty lies not only in its scale, but in its shape. Its spiral form, stretching across hundreds of thousands of light-years, gives us a clue about the dynamics of galaxies as living, evolving systems. The rotation of its disk, the pattern of its spiral arms, and the glow of its stars together tell a story of billions of years of cosmic evolution, of gas clouds collapsing under gravity, of stars forming, burning, and dying, and of the slow, majestic rotation that keeps the entire structure in motion. Through a telescope, Andromeda's appearance is breathtaking. You can make out its elongated oval shape, its bright nucleus, and even, with larger instruments, hints of those dusty lanes cutting across its disk, regions where gas and dust absorb starlight, creating dark streaks that stand out against the surrounding brilliance. Its two main satellite galaxies, Messier 32 or M32 and M110, appear nearby as small fuzzy companions gravitationally bound to their larger neighbor. Together they form a miniature galactic family, one that mirrors our own Milky Way and its smaller companions, the Magellanic Clouds. In the catalogue of the French astronomer Charles Messier, Andromeda was listed as M31, the 31st object he identified while searching for comets in the 18th century. Messier wasn't interested in galaxies themselves. At that time, their true nature was unknown, but he created his list to help astronomers avoid mistaking these fuzzy objects for comets. Ironically, that catalog went on to become one of the most famous astronomical references ever compiled, and M31 remains its crown jewel. Today, when astronomers look toward Andromeda, they see not just a galaxy, but a key to understanding how galaxies like ours form, evolve, and interact. Its structure offers a comparison to the Milky Way that helps us fill in the blanks about our own home galaxy, which we cannot observe from the outside. Andromeda's resemblance to the Milky Way also hints at the destiny the two galaxies share, a destiny that will bring them together billions of years from now in a slow, magnificent merger. The Andromeda Galaxy in all its brilliance stands as both a cosmic neighbor and a cosmic mirror. It is a gateway to understanding our place in the grand hierarchy of the universe, not just as inhabitants of a planet or a solar system, but as residents of a galaxy that itself is part of something far greater. When you look up on a dark, clear night and see that faint smudge hanging in the constellation of Andromeda, you are in a sense seeing across both space and time, gazing into a distant realm that mirrors our own on the grandest possible scale. And with that image in mind, we can now turn to the next essential question. Where exactly is the Andromeda Galaxy in the vast expanse of space, and how far must its light travel to reach us? Knowing what the Andromeda Galaxy is gives us context, but to truly grasp its magnitude, we must understand where it is. Because in astronomy, location is more than a matter of coordinates. It's a measure of time, scale, and perspective. The Andromeda Galaxy lies at a staggering distance of about 2.5 million light-years from Earth. That means the light we see from it tonight began its journey when our ancestors, the earliest members of the genus Homo, were just beginning to shape primitive tools out of stone. Every time you look at Andromeda, you're looking into the deep past, at a galaxy as it appeared long before human civilization or even modern humanity itself existed.
To put that distance into perspective, consider this. 1 light-year is the distance light travels in a single year, about 9.46 trillion kilometers, or roughly 5.88 trillion miles. So when we say Andromeda is 2.5 million light-years away, we mean its light has traveled 23 quintillion kilometers to reach us. These are numbers so enormous that they defy ordinary human intuition. If we tried to travel there using our fastest spacecraft, currently moving at around 60,000 kilometers per hour, it would take more than 40 billion years, many times longer than the age of the universe itself. From our vantage point on Earth, Andromeda resides in the constellation Andromeda, near the border with Pegasus, and is best visible in the northern hemisphere during autumn and early winter. Under a dark sky, far from the glow of artificial lights, you can actually spot it as a faint, elongated smudge, a soft whisper of light from a distant spiral galaxy. That hazy glow, subtle yet unmistakable, is the combined light of billions of stars, all blurred together by distance. To the naked eye, it doesn't look particularly large or bright, but appearances can be deceiving. In truth, Andromeda stretches across 3 degrees of the night sky, roughly 6 times the width of the full moon. The reason it seems smaller is because its light is spread so thinly across that vast area, making it faint to human vision. But why does its distance matter when we talk about its size? Because in astronomy, size and distance are inseparable. Measuring how large something appears in the sky is only the first step. To know how large it truly is, we need to know how far away it lies. This is one of the fundamental challenges of astronomy. we see everything in 2 dimensions, as points or shapes on a celestial sphere, and must infer the 3rd dimension, distance, using indirect methods. For Andromeda, astronomers have used several ingenious techniques to determine its distance. In the early 20th century, the groundbreaking astronomer Edwin Hubble identified Cepheid variable stars within Andromeda, stars that brighten and dim in predictable cycles. Because the period of their brightness variation is directly related to their intrinsic luminosity, Hubble could calculate their true brightness, compare it to how bright they appeared from Earth, and deduce Andromeda's distance. His calculations revealed something astonishing. Andromeda wasn't a nearby nebula within the Milky Way, as many had believed. It was an entirely separate galaxy, millions of light years away. This discovery revolutionized astronomy and expanded our conception of the universe from a single galaxy to a cosmos filled with billions of them. Today, we refined Andromeda's distance using even more precise tools, from observing red giant branch stars and novae to analyzing surface brightness fluctuations and measuring parallax through advanced space telescopes like Gaia. These methods converge on the same result. Andromeda's distance is about 2.5 million light-years, give or take a few percent. That number, 2.5, might seem abstract, but it carries immense significance. Because of that distance, the light we observe is ancient light, showing us Andromeda not as it is today, but as it was 2.5 million years ago. Every galaxy we see in the universe is effectively a time machine, and Andromeda gives us a glimpse into the Milky Way's nearest cosmic neighbor as it existed long before humanity's first civilizations. In fact, given the motion of galaxies through space, Andromeda's structure today is likely slightly different than what we currently observe. Stars have shifted, clusters have drifted, and perhaps even new stars have formed since the light we're now receiving first set out. Distance also defines how we perceive size. When astronomers say that Andromeda appears about 6 times the width of the moon in the sky, that's its apparent size. But using its distance, we can translate that apparent measurement into a physical size. We find that Andromeda's visible disk spans roughly 220,000 light-years from one end to the other, nearly double the width of the Milky Way's disk. Without knowing its distance, that number would be meaningless, because the same apparent size could correspond to a small nearby galaxy or a gigantic one much farther away. This interplay between distance and scale is what makes studying galaxies so challenging, yet so profound. In the universe, perspective is everything. The Andromeda Galaxy looks modest through a backyard telescope, but in truth, it's so vast that it would take light itself, the fastest thing in existence, more than 200,000 years to cross from one side of it to the other. And the more we study its distance, the more we realize how intimately connected it is to our own galactic story. The space separating the Milky Way and Andromeda is not a fixed gulf. It's shrinking. The 2 galaxies are moving toward each other, drawn by their mutual gravity, on a slow but inevitable collision course. That journey, which will culminate billions of years from now, is already subtly changing their relative distance every second. So when we talk about Andromeda's location, we're not talking about a static coordinate, but a dynamic relationship between 2 great galaxies dancing through space toward an ultimate union. The 2.5 million light-year gap that now separates us is immense beyond human measure. Yet in cosmic terms, it's the span of 2 neighbors approaching across a quiet, dark street, the first steps in a vast and beautiful encounter. And now that we've placed Andromeda in its proper place within the universe's grand geometry, it's time to ask an equally important question. When astronomers say a galaxy is this big, what exactly do they mean by size? When we speak about the size of the Andromeda Galaxy, or any galaxy for that matter, we're dealing with a concept that is far more complex than it seems. Unlike a planet or a star, a galaxy doesn't have a hard surface or a clear boundary where it ends and space begins. Instead, it gradually fades into the cosmic background, its stars thinning out until they're indistinguishable from the intergalactic void. So when astronomers ask, how big is Andromeda, they must first decide what they mean by big. The term size can describe several different things in a galaxy context, depending on what aspect we're measuring. For example, one of the most common ways astronomers define a galaxy's size is by its visible disk, the region we can see through telescopes where the majority of its stars, dust, and gas are concentrated. For Andromeda, this visible region spans an astonishing 220,000 light-years from edge to edge, making it nearly twice the diameter of the Milky Way's disk. When we look at photographs of Andromeda taken by space telescopes or long-exposure astrophotography, this bright, spiral-shaped disk is what we typically imagine when we think of the galaxy. But the visible disk is only the beginning of Andromeda's true extent. Beyond that glowing region of spiral arms lies a far more diffuse component, a stellar halo, composed of older, dimmer stars scattered in every direction. This halo doesn't emit much light, but it still belongs to the galaxy, extending its physical presence far beyond the bright disk. Some of these stars are remnants of smaller galaxies that Andromeda has consumed over billions of years, evidence of its long and violent history of galactic mergers. Depending on how faint a limit you use for detection, Andromeda's stellar halo could extend hundreds of thousands of light-years farther than the disk itself. Even that, though, doesn't mark the true boundary of Andromeda. The largest and most mysterious component of its structure is something we cannot see at all: its dark matter halo. Dark matter, though invisible, exerts gravity just like normal matter. It forms a vast spherical cloud around the visible galaxy, acting as an unseen skeleton that holds the whole structure together. Without this dark matter halo, Andromeda's stars and gas would rotate too quickly to remain bound. The galaxy would simply fly apart. Astronomers estimate that Andromeda's dark matter halo may stretch as far as 1 to 2 million light-years in radius, meaning it could extend almost halfway to the Milky Way. That's so immense that, in fact, the outer edges of Andromeda and the Milky Way's dark matter halos may already be touching. When people say the two galaxies will collide billions of years from now, the truth is that their invisible halos are already beginning to blend together, tugging subtly on each other through the deep cosmic dark. So depending on the context, the size of Andromeda can vary dramatically. If we're talking about its bright, visible disk, we mean a diameter of around 220,000 light-years. If we include its faint stellar halo, that number could climb to several 100,000 light-years. But if we take into account its dark matter halo, the true gravitational reach of the galaxy, then Andromeda might span millions of light-years from one side to the other. The challenge of defining galactic size isn't just a matter of semantics, it reflects the layered nature of galaxies themselves. A galaxy isn't a single object, but a vast, dynamic ecosystem of stars, gas, dust, and invisible matter, all interacting across mind-bending distances. Astronomers have to choose what kind of boundary they're referring to: the boundary of light, the boundary of mass, or the boundary of gravitational influence. This is why when two different sources describe Andromeda's size, the numbers may not always agree. One might refer to the visible disk and say 220,000 light-years across, while another might include the faint outskirts of stars or dark matter and give a much larger figure. Both are technically correct. They're just describing different aspects of the same enormous structure. To visualize this, imagine a city seen from space at night. The bright downtown core represents the luminous disk of Andromeda, teeming with stars. The sprawling suburbs and rural lights are like the stellar halo, fainter, older, but still part of the whole. And the invisible infrastructure beneath it all, the gravity that holds everything together, is the dark matter halo. The city limits of a galaxy in this analogy depend entirely on what we're trying to measure. This layered complexity makes galaxies like Andromeda endless fascinating.
Each component, the glowing spiral arms, the faint halo, and the invisible dark matter, tells a different story about the galaxy's formation, evolution, and structure. The visible disk shows where stars are forming now, the stellar halo reveals the scars of past mergers, and the dark matter halo defines the galaxy's hidden architecture. So when we ask, how big is Andromeda, we're asking not one question, but several at once. We're really asking, how far does its light reach? How far does its matter extend? And how far does its gravity rule? Each answer paints a different portrait of the same majestic galaxy, from a bright spiral island of stars to a vast, shadowy empire of matter stretching across intergalactic space. And now that we've understand how astronomers define size in these layered terms, we can take the next step in our exploration, to focus on the most visible and measurable part of Andromeda's grandeur, the sprawling luminous disk itself, the region that gives the galaxy its breathtaking beauty and that first captures the eye when we gaze upon it. Now that we've clarified what size can mean for a galaxy, let's focus on the most familiar and visually striking measure of all, Andromeda's visible diameter. This is the part of the galaxy that most people picture when they imagine it. The brilliant spiral disk filled with billions of stars, glowing nebula, and dark dust lanes that twist around its bright central core. When astronomers talk about Andromeda's visible size, they're referring to this shining, star-filled portion of the galaxy's shining face in the cosmic darkness.
The visible disk of the Andromeda Galaxy is truly immense. It stretches across an astonishing 220,000 light-years from one edge to the other, nearly twice the width of the Milky Way's disk, which measures about 100,000 to 120,000 light-years in diameter. To put that into perspective, if Andromeda were placed in the same position as our Milky Way, its spiral arms would extend far beyond the orbit of any known star in our galaxy, easily reaching past the large and small Magellanic Clouds, the Milky Way's satellite galaxies. That measurement, 220,000 light-years, is not a guess. It's the result of decades of detailed astronomical observations using both ground-based and space telescopes. Astronomers determine the extent of the visible disk by observing how far its stars and interstellar material can be detected before fading into the background of space. The edge isn't sharply defined. Instead, Andromeda's starlight gradually diminishes with distance from the center, much like city lights fading into rural darkness when viewed from an airplane. At the faintest levels of observation, those distant stars mark the practical edge of the visible galaxy, though its influence, as we've seen, extends much farther. When captured in long exposure photographs, Andromeda's disk reveals an intricate structure of spiral arms, vast, curved trails of stars, dust, and gas that wrap around its glowing nucleus. These arms are the hallmarks of a spiral galaxy, and they form patterns of incredible beauty and scale. In Andromeda, these spirals are not perfectly symmetrical. They appear slightly warped and twisted, a sign that gravitational interactions, possibly with its smaller satellite galaxies, M32 and M110, have tugged on its structure over cosmic time. Embedded within these spiral arms are regions of intense star formation, sometimes called stellar nurseries. These are massive clouds of gas and dust collapsing under gravity to form new generations of stars. When astronomers observe Andromeda in ultraviolet light or infrared wavelengths, these regions stand out like glowing beacons, marking where young, hot stars are igniting within dense nebulae. The visible disk is therefore not static. It's a dynamic, living system, continuously giving birth to stars while older ones burn out and die. The bright, central bulge of Andromeda, which dominates the heart of its visible disk, contains older, redder stars, remnants of earlier epochs of star formation. It's densely packed, glowing intensely in visible and infrared light, and at its very center lies a supermassive black hole with a mass tens of millions of times that of our Sun. This black hole anchors the galaxy gravitationally, influencing the motion of stars in its vicinity. Around it, a compact rotating disk of stars and gas spirals inward, mirroring the larger pattern on a smaller scale.
One of the most remarkable things about Andromeda's visible disk is how much of it we can actually see from Earth despite its enormous distance. To the unaided eye, it appears as a faint, elongated blur of light. But in reality, if our eyes were sensitive enough to detect its full brightness range, Andromeda would appear 6 times wider than the full moon in the night sky. Its apparent faintness comes not from its size, but from how thinly that light is spread across such a wide area. Every patch of brightness we see is the combined glow of millions of distant stars, their light merging together across millions of light years of space. What's especially fascinating is that Andromeda's visible disk is not a simple flat plane. Like the Milky Way, it's slightly warped, possibly due to gravitational interactions with nearby galaxies. The outer edges are tilted and rippled, as if stirred by tidal forces over time. This subtle warping gives the galaxy a sense of motion and depth when seen in high-resolution images, a reminder that galaxies are not rigid objects, but vast, fluid systems shaped by the gravitational choreography of the cosmos. Comparing Andromeda's disk to our Milky Way gives us a clearer sense of scale. If the Milky Way were reduced to the size of a standard dinner plate, Andromeda's visible disk would be roughly the size of a large serving tray. Its mass and luminosity both reflect this difference. Andromeda contains more stars, more gas, and likely more dust than our galaxy. Astronomers estimate that it may host over 1 trillion stars, while the Milky Way contains around 200 to 400 billion. That difference in stellar population contributes directly to its brightness. Andromeda is the brightest galaxy visible from Earth beyond our own, even with the naked eye. Observing Andromeda's visible disk gives scientists crucial insights into the life cycle of galaxies. By studying how stars move within it, astronomers can infer the galaxy's rotation curve, how fast stars orbit the center at different distances. Interestingly, these observations revealed one of the earliest pieces of evidence for dark matter. Stars in the outer parts of Andromeda's disk move faster than they should if only visible matter were present, implying the presence of an unseen mass that extends far beyond what we can detect directly.
So, when we say Andromeda's visible disk is 220,000 light-years across, we're describing the glowing core of an even larger system, the bright, observable structure that defines its character, but not its limits. It's a luminous canvas stretched across the void, containing within it the full cycle of stellar evolution, from newborn stars just igniting to ancient red giants fading into obscurity. Standing beneath the night sky and realizing that faint smudge of light represents such an immense expanse is humbling. Every pixel of an image of Andromeda contains thousands of suns. Every faint glow marks the light of entire star clusters and nebulae. The visible disk we admire from afar is, in truth, a cosmic metropolis of breathtaking proportions, one that dwarfs our own galactic home in both scale and splendor. And now that we've explored the immense breadth of Andromeda's visible face, it's time to place that size in context. To truly appreciate just how large Andromeda is, we must compare it directly to the galaxy we call home, our Milky Way, and see how these two great spirals measure up against each other in the vastness of space. When we stand under the stars and think of the Milky Way, our own galaxy, the grand spiral of light that wraps across the night sky, it feels enormous beyond comprehension. Yet, when we compare it to the Andromeda Galaxy, that sense of scale shifts dramatically. Andromeda, magnificent and distant as it is, makes our galactic home seem almost modest in comparison. The Milky Way's visible disk measures roughly 100,000 to 120,000 light-years across. That's already vast. It means that even traveling at the speed of light, it would take 100,000 years to go from one edge of our galaxy to the other. But when we set that beside Andromeda's 220,000 light-year diameter, the contrast becomes stunning. Andromeda is nearly twice the size of the Milky Way in visible width, and it contains roughly 2 to 3 times more stars. Astronomers estimate that our galaxy holds somewhere between 200 billion and 400 billion stars, while Andromeda may contain over 1 trillion. Its total luminosity, the combined light of all its stars, outshines the Milky Way by a significant margin.
If both galaxies were placed side by side, Andromeda's spiral arms would stretch far beyond the Milky Way's boundaries, extending deep into space where our galaxy's star fields begin to fade. The difference isn't just about numbers, it's also about appearance. While both galaxies are spiral galaxies, their structures are distinct in subtle but telling ways. The Milky Way is classified as a barred spiral galaxy, meaning it has a bar-like structure of stars running through its core with its spiral arms extending from the ends of that bar. Andromeda, on the other hand, is classified as an SA-S spiral galaxy, a designation meaning it has well-defined, tightly wound spiral arms without a strong central bar. Its spiral arms are broader, more open, and studded with bright blue clusters of young stars and pinkish nebulae. If we could view both galaxies from outside, as cosmic observers looking down from above, Andromeda would appear as a grander, more sprawling disk, its spiral arms sweeping wider, its central bulge larger and brighter. The Milky Way, by contrast, would seem more compact, its disk slightly thicker, its spiral arms less open and more fragmented. Both are elegant in their own right, but Andromeda's proportions make it look like the older, larger sibling in a family of galactic giants. Yet, despite these differences, the two galaxies share many similarities that bind them together as cosmic kin. Both have roughly the same overall mass, on the order of 1 trillion times the mass of the Sun, though some recent studies suggest the Milky Way may have a bit more dark matter than previously thought, narrowing the gap between them. Both galaxies also host supermassive black holes at their centers, each with masses of tens of millions of suns. Both are surrounded by halos of globular clusters, dense ancient groups of stars that orbit far beyond the visible disks, relics from the early days of galaxy formation. In essence, the Milky Way and Andromeda are mirror images of each other across the void, two massive spiral galaxies with similar compositions, similar histories, and, as we'll explore later, a shared destiny. But in terms of pure visible size and stellar content, Andromeda holds the advantage. If we were to scale the Milky Way down to the size of a dinner plate, Andromeda would be about the size of a serving tray, with its spiral arms reaching further, its disk brighter, and its stellar population denser. Its vastness gives it a stronger gravitational pull, one powerful enough to attract and retain more satellite galaxies, smaller companions that orbit it like moons around a planet. This gravitational dominance is one reason why Andromeda's sphere of influence in the local group, the small cluster of galaxies that includes both Andromeda and the Milky Way, is so extensive.
But despite Andromeda's larger size, the Milky Way may not be as far behind as once thought. For many years, scientists believed Andromeda was clearly the heavyweight of the local group. Recent observations using the Gaia Space Observatory and other high-precision instruments has suggested that our Milky Way might be more massive than previously estimated, largely because of the amount of dark matter surrounding it. This means that while Andromeda may appear larger and brighter in visible light, the Milky Way could rival or even exceed it in total mass when invisible matter is considered. Still, in terms of visible scale, there is no contest. Andromeda's glowing disk, sprawling across hundreds of thousands of light-years, dwarfs our own galactic domain. If the Milky Way were placed within Andromeda, its spiral arms would fit comfortably inside the inner regions, leaving vast outer expanses of Andromeda's disk stretching far beyond. The difference in size is not a subtle one. It's dramatic and humbling, a reminder that even our immense galaxy is but one variation in a grand spectrum of cosmic structures. And yet, this comparison carries a deeper significance. Despite its greater size, Andromeda isn't some unreachable giant. It's our nearest major galactic neighbor, the closest mirror we have to study our own structure from afar. Through Andromeda, astronomers learn about the Milky Way by analogy, by studying what we can see there and applying those lessons here. Every observation of Andromeda's spiral arms, dust lanes, and star clusters helps us infer what our own galaxy might look like if seen from an outside vantage point. In a sense, comparing Andromeda to the Milky Way isn't just about numbers, it's about perspective. The two galaxies are part of the same cosmic family, bound by gravity, destined to meet, and shaped by similar processes over billions of years. Their differences in size tell us about variation in galactic evolution, how some galaxies grow larger by merging with others, accumulating mass over eons, while others remain smaller and quieter.
So when we look up at that faint blur in the constellation Andromeda, we're not just looking at a larger galaxy. We're looking at a preview of our own fate, a glimpse of what our Milky Way might become in the far future, when the two collide and merge into something entirely new. And as we continue our exploration, it's time to peer closer at what fills that enormous space, to look within Andromeda's vast disk and understand what actually makes up its size. The billions of stars, swirling dust lanes, and luminous clouds of gas that together form one of the grandest structures in the known universe. When we speak of Andromeda's immense size, its 220,000 light-year-wide disk stretching across the void, that number alone tells only part of the story. To truly comprehend its magnitude, we have to look within it, to explore what fills that vast expanse. Because Andromeda is not just an empty structure of light, it is a thriving, intricate ecosystem of billions of stars, swirling rivers of gas and dust, and vast star-forming regions where new suns are being born every day. Within that colossal disk lies a dynamic world of motion, energy, and transformation, a city of stars on a galactic scale. At its heart, Andromeda's visible structure is built around its spiral arms, the sweeping, luminous bands that wind gracefully around the galaxy's central bulge. These arms are the highways of galactic life, where gravity and rotation shape the distribution of stars, gas, and dust. The spiral pattern isn't a fixed structure like the wheel's spokes. Rather, it's a density wave, a region of higher concentration that moves through the disk, compressing clouds of interstellar gas as it goes. This compression acts like a cosmic trigger, igniting the birth of new stars in massive glowing clusters. The star-forming regions in Andromeda are some of the most spectacular in the nearby universe. One of the largest and most famous is NGC 206, a sprawling region of brilliant, young blue stars located in one of Andromeda's spiral arms. It's visible even through moderate telescopes as a bright patch within the disk, a stellar nursery tens of thousands of light-years across. These young stars burn hot and bright, illuminating the surrounding gas clouds and giving the galaxy much of its characteristic bluish tint when seen in visible light. Their intense ultraviolet radiation excites nearby hydrogen atoms, causing them to glow in soft red hues, a hallmark of star formation that astronomers detect using specialized filters and instruments. The contrast between these bright, youthful regions and the darker areas of the disk tell another part of the story. Threaded throughout Andromeda's spirals are vast dust lanes, enormous clouds of interstellar dust and molecular gas that absorb and scatter starlight, appearing as dark, shadowy streaks against the galaxy's glowing background. These dust lanes aren't just empty voids, they are the raw material for future generations of stars. In the infrared spectrum, where dust becomes transparent, astronomers can peer into these regions and see the hidden processes of star birth unfolding. Collapsing clouds of gas-forming protostars, surrounded by swirling disks of material that may become planetary systems one day. Closer to the center, the character of Andromeda changes. Its central bulge, the bright, egg-shaped region at the core, is filled with older, redder stars, remnants from an earlier epoch of star formation. This bulge spans tens of thousands of light-years and shines with the accumulated light of billions of ancient suns, densely packed together in orbits that swirl around the galaxy's hidden core. Nestled within this central region lies a supermassive black hole, estimated to have a mass of about 100 million times that of our Sun. Around it orbits a dense cluster of stars forming a compact, bright nucleus that glows fiercely in visible and infrared light. The black hole itself, though invisible, exerts a powerful influence on its surroundings. Astronomers have observed stars whipping around it at incredible speeds, their motion betraying the presence of the unseen giant. Occasionally, when a star or cloud of gas ventures too close, the black hole's gravity tears it apart, heating the debris and sending bursts of X-rays streaming across the galaxy. Though relatively quiet today, Andromeda's central black hole was likely far more active in the past, perhaps shining as a quasar billions of years ago when galaxies were young and collisions were common.
Extending outward from the core through the spiral arms are countless stellar populations of every kind imaginable, from brilliant blue giants that live for only a few million years to dim red dwarfs that will burn for trillions.
Between them drift aging red giants, supernova remnants, and globular clusters, dense spherical collections of stars that orbit far above and below the disk like cosmic beehives. These clusters are among the oldest components of the galaxy, containing some of the first stars to have formed more than 10 billion years ago. But stars and dust are not the only ingredients that give Andromeda its structure. The galaxy's disk also contains enormous clouds of interstellar gas, mostly hydrogen, that stretch for thousands of light years. These clouds are mapped in radio wavelengths by observing the 21-centimeter emission line of neutral hydrogen, a signal that reveals their motion and distribution. This radio mapping allows astronomers to trace the full shape of Andromeda's disk, even in regions too faint to see in visible light. It's through this technique that scientists confirmed the galaxy's vast 220,000 light-year span, revealing spiral arms and outer structures that optical telescopes could not detect. The interplay between stars, dust, and gas gives Andromeda its living texture, a galaxy constantly in motion, with material cycling between different forms. Dying stars expel gas and heavier elements into space through stellar winds and supernova explosions. That gas mixes with interstellar dust to form new molecular clouds. In time, those clouds collapse under gravity to create new stars, continuing the endless cycle of stellar evolution that has defined the galaxy for billions of years. Every glowing star in Andromeda is part of that story, the visible result of an ancient chain of cosmic recycling stretching back to the galaxy's birth. And Andromeda's disk isn't uniform either. Observations have shown subtle ripples and asymmetries across its structure, faint distortions likely caused by past interactions with smaller galaxies. When one of these dwarf companions drifts too close, its gravity tugs on Andromeda's stars in gas, creating waves that ripple across the disk. These gravitational encounters leave long-lasting imprints, warped spiral arms, ring-like structures, and streams of stars that stretch far beyond the main body of the galaxy. Some of Andromeda's outermost stars are thought to have been stolen from these smaller galaxies, captured during past collisions that helped it grow. Taken together, all these components, the stars, gas, dust, clusters, and black hole, form the visible architecture of Andromeda. It's a complex, layered system where every part, from the glowing arms to the dark dust lanes, plays a role in shaping the whole. The galaxy's size is not just a matter of its diameter, but of the richness and depth of what fills that space, a symphony of light and gravity performed on a scale so vast it defies imagination. When we gaze at Andromeda through a telescope, we're not just seeing a flat disk of light. We're looking into a three-dimensional world of cosmic structure, alive with the birth and death of stars, the swirling of dust clouds, and the invisible pull of gravity that binds it all together. That's what truly fills its enormous 220,000 light-year span. Not empty space, but the endless processes of creation and transformation that define galaxies themselves. And as we look beyond the visible, into the regions we cannot see with the naked eye, we discover that Andromeda's size extends far beyond this glowing disk. Surrounding it lies a vast and invisible component that adds even more to its scale and mystery: the dark matter halo, a shadowy realm that stretches for millions of light years and holds the galaxy in its invisible grip. When we look at Andromeda's luminous spiral disk, its glowing arms and radiant core, we're seeing only the surface of a much deeper, more mysterious structure. Beyond that bright expanse of stars and dust lies a vast invisible component that dominates the galaxy's true mass and size: the dark matter halo. This halo, unseen but profoundly influential, extends far beyond the visible boundaries of the galaxy, shaping its motion, anchoring its gravity, and determining how it interacts with the universe around it. The dark matter halo is not just a peripheral feature, it's the very foundation of Andromeda's structure. Astronomers estimate that while the stars, gas, and dust we can observe make up only about 10% of the galaxy's total mass, the remaining 90% is dark matter, an elusive, invisible substance that neither emits nor absorbs light. We can't see it directly, but we know it's there because of its unmistakable gravitational effects. Without it, Andromeda's visible disk simply couldn't exist as it does. The evidence for this halo comes from the rotation curve of the galaxy, a graph showing how fast stars orbit the center at different distances. According to the laws of Newtonian physics, if most of Andromeda's mass was concentrated in its visible stars, the orbital speeds of stars in the outer regions should decrease with distance from the center, much like planets in our solar system orbit more slowly the farther they are from the sun. But when astronomers measured those speeds, they found something astonishing. The stars at Andromeda's outskirts were moving just as fast as those closer to the core.
That observation defied explanation, unless there was additional, unseen mass spread throughout and far beyond the visible galaxy. This invisible mass, exerting its gravitational pull, prevents the outer stars from flying off into intergalactic space. Thus, the concept of dark matter emerged, not as a speculation, but as a necessary reality to explain the observed behavior of galaxies like Andromeda. So, just how far does Andromeda's dark matter halo reach? Observations and computer simulations suggest that it could extend between 1 and 2 million light-years from the galaxy's center, nearly 10 times farther than its visible disk. If we could somehow see this halo, it would dwarf the glowing spiral we recognize as Andromeda, forming an enormous ghostly sphere enveloping it on all sides. To visualize its scale, imagine Andromeda's bright disk, 220,000 light-years wide, as a coin lying at the center of a sphere the size of a planet. That vast, invisible sphere of dark matter would stretch outward into the cosmic void, overlapping with the outer regions of the Milky Way's own dark matter halo. In fact, many astronomers believe the halos of our two galaxies are already touching, quietly merging at the edges long before the galaxies themselves will collide billions of years from now. Though dark matter makes up most of Andromeda's mass, we still don't know exactly what it is. It doesn't emit radiation, doesn't reflect light, and doesn't interact with ordinary matter except through gravity. Some theories propose that dark matter consists of exotic, as yet undetected particles, perhaps WIMPs, weakly interacting massive particles, or axions, that drift through the cosmos like invisible dust. Others suggest it could be a manifestation of unknown physics, a clue to something deeper in our understanding of gravity itself. Whatever its nature, dark matter acts as the scaffolding of the universe, the invisible framework upon which galaxies form and grow. In the case of Andromeda, its dark matter halo not only defines the galaxy's outer boundary, but also governs its dynamics. It shapes how stars move, how gas flows through the disk, and even how the galaxy interacts with nearby companions like M32 and M110. The halo's gravitational pull is what binds these smaller galaxies to Andromeda, keeping them in orbit as part of its vast gravitational empire. Astronomers have detected evidence of this halo's presence through several techniques. By studying the motions of distant globular clusters and satellite galaxies, scientists can infer how much invisible mass must exist to account for their orbits. These measurements consistently point to a massive extended halo stretching hundreds of thousands, even millions of light-years outward. Observations using gravitational lensing, where Andromeda's mass bends the light of more distant galaxies, also reveal the faint fingerprints of dark matter scattered throughout its periphery. The halo's influence extends even beyond Andromeda's immediate neighborhood. Its immense gravitational field plays a role in shaping the dynamics of the entire local group of galaxies, the small cluster of about 50 galaxies that includes both Andromeda and the Milky Way. Within this cosmic community, Andromeda's dark matter halo acts like a vast gravitational anchor, exerting a quiet but profound influence across intergalactic space. It's humbling to realize that most of Andromeda's mass, and therefore most of what it is exists beyond the reach of our eyes and even our most powerful telescopes. The glowing spiral we admire through the night sky is merely the tip of the iceberg, the visible trace of a much larger hidden structure. If we could perceive dark matter as light, Andromeda would appear not as a flat luminous disk, but as a colossal, spherical cloud with a faint glowing heart suspended inside. This invisible halo is also the reason Andromeda and the Milky Way are destined to merge. Over billions of years, the mutual attraction between their overlapping halos will draw them inexorably together, pulling their visible structures into a slow, spiraling collision that will reshape both galaxies. The dark matter halos will merge first, forming a single massive gravitational well that will eventually pull in all the visible material, stars, dust, and gas to create a new, larger galaxy. So when we talk about Andromeda's true size, we have to remember that it extends far beyond what we can see. Its 220,000 light-year wide disk may define its visible form, but its dark matter halo, possibly a million or more light-years across, defines its true reach. And in that immense, unseen expanse lies the gravitational bond that connects Andromeda not just to its own stars, but to the Milky Way itself, across the silent gulf between them.
And as we continue to explore the galaxy's hidden architecture, the next question naturally follows. How do astronomers actually measure something so vast, so distant, and so complex? How can we know the size, structure, and motion of a galaxy millions of light years away? The answer lies in the powerful tools and ingenious methods astronomers use to decode the cosmos itself. Measuring the size of something as immense and distant as the Andromeda Galaxy is one of the great triumphs of modern astronomy, a feat that combines ingenuity, precision, and decades of technological advancement. Unlike a mountain or a planet, a galaxy doesn't have a fixed edge you can point to or measure with a ruler. Instead, astronomers must rely on subtle clues: the light of stars, the motion of gas, the faint radio whispers from hydrogen, to determine how far Andromeda extends, how massive it is, and how fast it moves through space. To understand how scientists do this, we first have to appreciate a fundamental truth. Light is information. Every photon of light that reaches us from Andromeda carries a coded message about its source, about the motion, temperature, and composition of the stars and gas that emitted it. Astronomers have learned to decode this message using a technique called spectroscopy, which splits light into its component wavelengths, much like a prism creating a rainbow. In that spectrum, tiny shifts and patterns reveal enormous truths. When the light from Andromeda stars is analyzed, astronomers notice slight changes in the wavelengths of specific absorption lines, the fingerprints of elements like hydrogen, helium, and calcium. These lines shift toward the blue end of the spectrum, a sign that Andromeda is moving toward us. This phenomenon, known as blue shift, occurs because the light waves are compressed as the galaxy approaches. Measuring this shift not only tells astronomers Andromeda's velocity, about 110 kilometers per second toward the Milky Way, but also allows them to track how individual regions within the galaxy move. The rotational motion of its disk, the behavior of its spiral arms, and even the motion of its outermost stars. By mapping how fast stars and gas orbit at different distances from Andromeda's center, astronomers can infer how much mass lies within each orbit. This relationship, known as the rotation curve, is the key to determining the galaxy's true extent. If Andromeda's visible matter, its stars and gas, were all that existed, the outer stars would orbit more slowly than those closer in, much like the outer planets in our solar system move slower than the inner ones. But observations tell a different story. The stars at the edges of Andromeda's disk are orbiting almost as fast as those near the center. This means there must be an enormous amount of unseen mass, the dark matter halo we discussed earlier, extending far beyond the visible edge.
The data that reveal this don't come from optical telescopes alone. Astronomers also rely on radio telescopes, which detect signals invisible to human eyes but essential for understanding galactic structure. One of the most valuable of these is the 21 centimeter of neutral hydrogen gas, HI. Hydrogen is the most abundant element in the universe, and it emits a faint but detectable radio wave at this specific wavelength when the spins of its electron and proton flip relative to each other. By tuning into this frequency, astronomers can map the distribution of hydrogen throughout Andromeda's disk, even in regions that are too faint or obscured by dust to be seen in visible light. Using arrays of radio dishes like the Very Large Array in New Mexico and other observatories around the world, scientists have traced Andromeda's hydrogen gas far beyond its bright spiral arms. These radio maps showed that the galaxy's disk stretches much farther than optical telescopes can detect, confirming a total diameter of roughly 220,000 light-years, and in some areas, revealing filaments of gas extending even farther outward, possibly linking the galaxy to its surrounding environment. But measuring size isn't just about mapping its outline. It's also about measuring depth and distance, determining how far Andromeda truly is from us, and thus how its apparent size translates into real dimensions. For this, astronomers turn to a variety of standard candles, celestial objects whose intrinsic brightness is known, allowing their distance to be calculated from how bright they appear.
One of the most important types of standard candles used for Andromeda is the Cepheid variable star. These stars pulsate in a regular rhythm, and the period of their pulsation directly correlates with their true luminosity. By measuring how bright a Cepheid appears from Earth and comparing it to its known luminosity, astronomers can calculate its distance, and therefore the distance to the galaxy it inhabits. Edwin Hubble himself used Cepheid variables in the 1920s to prove that Andromeda lay far beyond the Milky Way, establishing that it was an entirely separate galaxy. Today, modern telescopes and instruments like the Hubble Space Telescope and the Gaia Space Observatory have refined those measurements to extraordinary precision. By combining observations of Cepheids, red giant stars, and even novae, exploding stars that serve as temporary standard candles, astronomers have pinned Andromeda's distance at about 2.5 million light-years, with an uncertainty of less than a few percent. Another powerful technique involves studying surface brightness fluctuations, tiny variations in the light across the galaxy's image caused by the random distribution of stars. By analyzing the statistical properties of these fluctuations, astronomers can estimate distance and, by extension, refine the scale of Andromeda's features. When all these measurements, optical, infrared, and radio, are combined, they form a cohesive picture. Astronomers can not only map Andromeda's spiral arms and disk, but also reconstruct its three-dimensional structure, revealing how it's tilted toward us, how its outer regions warp and twist, and how its rotation behaves at every level. In fact, by observing subtle changes in star positions over time, modern instruments are even beginning to detect proper motion. Andromeda's slow drift across the sky as it moves toward the Milky Way, a monumental achievement given its immense distance. To ensure these measurements are accurate, astronomers also simulate Andromeda's dynamics using computer models. These simulations take into account the observed motion of stars, the distribution of gas, and the gravitational effects of dark matter, allowing scientists to predict how the galaxy's structure should appear and evolve. When the models match observations, it confirms that our understanding of Andromeda's size and composition is on the right track. Through this combination of spectroscopy, radio astronomy, standard candles, and modeling, we have built a remarkably detailed understanding of Andromeda. Not just its visible shape, but its hidden mass, its motion, and its cosmic scale. What once appeared to ancient observers as a faint patch of light in the constellation Andromeda
is now revealed as a galaxy of nearly unimaginable complexity, mapped in exquisite detail by instruments that turn faint photons into cosmic cartography. And as we trace the evolution of how these measurements came to be, from the early days of astronomy to the modern age of precision science, we uncover a story that's as much about human curiosity as it is about the galaxy itself. Because there was a time, not so long ago, when no one even knew Andromeda was a galaxy at all. For most of human history, the Andromeda Galaxy was not recognized as a galaxy at all. To early astronomers, it was simply a curious patch of light in the sky, a faint, misty cloud that defied clear explanation. Long before telescopes revealed the structure of the universe, the Andromeda Nebula, as it was called, lingered as one of the great mysteries of the heavens. It was visible to the naked eye under dark skies, but even the most powerful instruments of the 17th and 18th centuries could not resolve it into individual stars. To those early observers, it seemed like a glowing smear, a strange, unresolved object that didn't fit neatly into any known category of celestial body. The earliest recorded mention of Andromeda comes from around 965 CE, when the Persian astronomer Abd al-Rahman al-Sufi described it in his book of fixed stars. He referred to it as a small cloud in the constellation of Andromeda, noting its position and faint diffuse appearance. For centuries after that, it remained little more than a curiosity, an odd cloud-like feature cataloged by star watchers, but not understood. It wasn't until the invention of the telescope that Andromeda began to take on new significance. In 1612, the German astronomer Simon Marius became the first to observe it through a telescope. He described it as a nebulous object, a term used at the time to describe anything that appeared cloudy or fuzzy in the night sky. The word nebula itself simply meant cloud, and in centuries that followed, astronomers would discover hundreds of such nebulae, cataloging them as mysterious celestial patches that might be clusters of stars, glowing gas clouds, or something else entirely. By the 18th century, astronomers like Charles Messier and William Herschel began creating catalogs of these objects, partly to help avoid confusing them with comets. In 1764, Messier added the Andromeda Nebula to his list as Messier 31, M31, a now famous designation still used today. Though Messier didn't know what it truly was, his catalog ensured that the Andromeda Nebula would become one of the most studied and discussed objects in the night sky. For a long time, astronomers assumed that the Andromeda Nebula, and others like it, lay within our own Milky Way. The prevailing belief was that the Milky Way constituted the entire universe, a vast but finite collection of stars surrounded by empty space. Anything visible in the sky, they thought, must therefore be part of our galaxy. But not everyone was convinced. Some astronomers suspected that objects like Andromeda might actually be island universes, galaxies in their own right, far beyond the boundaries of the Milky Way.
This debate reached its peak in the early 20th century and came to be known as the Great Debate. In 1920, two prominent astronomers, Harlow Shapley and Heber Curtis, famously argued over the true nature of spiral nebulae like Andromeda. Shapley maintained that the Milky Way was so large that these nebulae must lie within it. Curtis, on the other hand, argued that they were independent galaxies, separate universes scattered throughout space. The question remained unresolved until a young astronomer named Edwin Hubble entered the picture. Working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, then the most powerful telescope in the world, Hubble set out to examine Andromeda in unprecedented detail. His goal was to find Cepheid variable stars, those pulsating beacons whose rhythmic brightness could be used to measure distance. In 1923, Hubble found exactly what he was looking for. Using photographic plates taken of the Andromeda Nebula, he identified several Cepheid variables within it. By calculating their distances, he made a stunning discovery. These stars were far too distant to be part of the Milky Way. In fact, they were more than 900,000 light-years away, far beyond the known limits of our galaxy,
later refined to about 2.5 million light-years. This single observation changed everything. Hubble had proved that the Andromeda Nebula was not a nebula at all, but an entirely separate galaxy, a vast system of stars in its own right. His findings, published in 1924, shattered the notion that the Milky Way was the whole universe. Overnight, the cosmos expanded from one galaxy to billions. It's hard to overstate how revolutionary that moment was. Before Hubble's discovery, humanity's cosmic map was confined to a single island of stars. Afterward, the universe became an ocean of galaxies, each potentially home to billions of stars and worlds. The Andromeda Galaxy became the first clear evidence that our Milky Way was just one among many, a revelation that transformed astronomy and our place within the cosmos. Hubble's work didn't end there. He went on to show that other galaxies were moving away from us, leading to the discovery of the expanding universe, the foundation of modern cosmology and the Big Bang Theory. But it all began with Andromeda. That faint smudge in the night sky, long thought to be a simple cloud, turned out to be an entire galaxy, a colossal structure so vast that its light takes millions of years to reach us. Even today, Andromeda stands as a symbol of that breakthrough, a reminder of how a single observation can rewrite our understanding of everything. Every time we gaze at its soft glow, we are, in a sense, looking at the very object that opened humanity's eyes to the scale of the universe. And with that realization of Andromeda's true identity came a deeper appreciation for its immense mass and power. For size is not just measured in distance, but in the total amount of matter a galaxy holds. The stars, gas, dust, and dark matter bound together by gravity. To understand just how massive Andromeda really is, we must next turn to its weight in the cosmic balance, the mass that defines its strength and scale in the universe. When we speak of how big the Andromeda Galaxy is, we often think of distance, its colossal 220,000 light-year wide disk stretching across the void. But in astronomy, size is not only about width. It's also about mass, the total amount of matter a galaxy contains, both visible and invisible. Andromeda's true magnitude becomes even more astonishing when we consider just how much it weighs in the grand cosmic scale. The Andromeda Galaxy is a titan among galaxies, containing an estimated 1 trillion stars, more than twice as many as the Milky Way. Each of those stars varies in size and brightness, from tiny red dwarfs that barely shine to immense blue giants that burn millions of times more brightly than our sun. If we could somehow count every one of them, we would find that Andromeda's combined stellar mass is roughly 400 billion times the mass of the sun, just in ordinary stars alone. But the story doesn't end with starlight. When we include the vast reservoirs of interstellar gas and dust, the galaxy's mass grows even larger. Massive clouds of hydrogen and helium swirl through its spiral arms, feeding new generations of stars. These gaseous regions make up about 10 to 15% of the galaxy's visible mass. And then there's the dark matter, the mysterious invisible substance that makes up the vast majority of Andromeda's weight. When all these components are added together, astronomers estimate that Andromeda's total mass is around 1 trillion solar masses. That is, roughly 1 trillion times the mass of our Sun. Some recent studies, depending on the method used, place it slightly lower or higher, in the range of 800 billion to 1.5 trillion solar masses. But the scale is still staggering. It's this enormous gravitational heft that binds the galaxy together, keeps its stars in orbit, and holds its smaller companion galaxies firmly within its influence. To appreciate that mass, consider this. If you could somehow scoop up all the stars, planets, gas, dust, and dark matter in Andromeda and place it on one side of a balance scale, you would need about 10 billion Milky Way-sized solar systems on the other side to even the weight. That's the kind of cosmic gravity we're dealing with. An invisible force so immense that it sculpts the motion of smaller galaxies around it and subtly tugs on our own Milky Way across 2.5 million light-years of space. Astronomers have calculated Andromeda's mass in several ingenious ways. One method involves observing the orbital velocities of stars and gas within its disk. The faster objects move under gravity, the greater the mass required to keep them bound. By mapping these velocities, through the Doppler shifts of spectral lines, scientists can determine how much matter lies inside any given radius of the galaxy. Another approach measures the motion of Andromeda's satellite galaxies and globular clusters. Their orbits act like distant test particles, tracing the reach of Andromeda's gravitational field. These studies have consistently shown that the galaxy's visible matter, the stars and gas we can see, accounts for a small fraction of its total gravitational mass. The rest, about 85 to 90%, is dark matter, spread throughout a vast halo that extends well beyond the visible disk. Without this invisible component, Andromeda's outer stars would orbit too fast to remain bound. The galaxy would simply fly apart. Instead, the presence of dark matter holds everything together, shaping the structure we see today. To understand what 1 trillion solar masses really means, we can imagine it in smaller, more familiar terms. The Sun itself, though enormous by human standards, is a relatively average star, containing about 330,000 times the mass of Earth. A trillion suns would therefore equal roughly 330 quadrillion Earths, a number so large that it exceeds the number of grains of sand on every beach on our planet by a factor of billions. That is the scale of Andromeda's gravitational might.
This immense mass has profound implications for the galaxy's behavior and future. It's what enables Andromeda to dominate the local group, the small cluster of about 50 galaxies that includes the Milky Way, the Triangulum Galaxy, M33, and many smaller dwarf galaxies. Andromeda's gravitational field reaches across millions of light years, subtly influencing the motions of its neighbors, including our own. In fact, it's that gravitational attraction, driven by Andromeda's massive dark matter halo, that's pulling the Milky Way and Andromeda toward each other, setting them on a slow but inevitable collision course. The mass of Andromeda also helps explain its appearance. More mass means more gas and dust available for star formation, and indeed, Andromeda is rich with young, luminous stars, particularly in its spiral arms. These bright, hot stars burn fiercely and live short lives, constantly renewing the galaxy's brilliance. Meanwhile, older stars populate its bulge and halo, contributing to its total mass but shining less brightly. The balance between these stellar populations gives Andromeda its characteristic glow, a mix of youthful blue light and ancient amber tones. Interestingly, new research using data from the Gaia spacecraft and advanced computer modeling has revealed that Andromeda's mass may not have been built all at once. It likely grew through mergers and collisions with smaller galaxies over billions of years, absorbing their stars and dark matter into its expanding structure. Each merger added to its weight, fueling bursts of star formation and reshaping its spiral pattern. And this way, Andromeda is not a static object, but a living, evolving entity, one that continues to grow as it consumes its smaller companions. When astronomers compare Andromeda's mass to that of the Milky Way, the two are surprisingly close. For many years, Andromeda was thought to be the clear heavyweight, perhaps twice as massive as our own galaxy. But more recent measurements of the Milky Way's dark matter halo suggested the two may be roughly equal in mass, differing by no more than 10 to 20%. If true, it means that when they eventually merge, neither will completely dominate the other. Instead, they will combine their trillion solar masses into a new, larger elliptical galaxy. Still, Andromeda's enormous gravitational presence is undeniable. It's the anchor of our cosmic neighborhood, the largest and most massive galaxy within several million light years. Its trillion solar mass weight gives it not only physical structure, but also cosmic influence, shaping the environment of the local group and determining the ultimate fate of its neighbors. And while this mass gives Andromeda stability, it also defines its beauty. Each one of those trillion stars, from the faintest red dwarf to the most luminous supergiant, contributes a piece of light to the soft, glowing oval we see from Earth. It's humbling to realize that when we look at that faint blur in the night sky, we are seeing the collective radiance of a trillion suns, held together by a trillion times the gravity of our own.
But Andromeda's structure doesn't end where its bright disk fades. Beyond the visible stars lies another fainter component, a stellar halo of ancient, dispersed stars that stretches into the depths of intergalactic space. This faint, ghostly envelope adds yet another layer to the galaxy's vast scale and tells the story of its long and tumultuous history. When we picture a galaxy like Andromeda, we often imagine a clean, distinct shape, a magnificent spiral of glowing arms wrapped around a bright center. But in reality, galaxies don't end neatly where the light appears to fade. Beyond the luminous disk, beyond even the faintest traces of its spiral arms, lies an enormous, nearly invisible realm, the stellar halo. This halo is Andromeda's outermost skin, a vast, diffuse sphere of ancient stars that stretches far beyond its main disk, blending gradually into the emptiness of intergalactic space. The stellar halo of Andromeda is a ghostly, ethereal structure, faint and difficult to detect. It extends hundreds of thousands of light years in every direction, much farther than the visible disk, and contains some of the oldest stars in the galaxy. These stars are sparse, widely scattered, and dim compared to the dense concentrations of light in the spiral arms. Yet, they hold the key to understanding Andromeda's ancient past. The halo is, in a sense, a cosmic fossil field, preserving evidence of billions of years of galactic evolution. Unlike the orderly disk, where stars move in relatively circular orbits, the stars in the halo follow elongated, random paths, crisscrossing in all directions. This chaotic motion is the legacy of Andromeda's violent history, a history of collisions and mergers with smaller galaxies. Over billions of years, Andromeda has grown by consuming these dwarf companions, tearing them apart through gravitational forces and scattering their stars into long, thin streams that eventually blend into the diffuse glow of the halo. Astronomers have actually observed some of these stellar streams around Andromeda. Using deep imaging surveys such as the Pan-Andromeda Archaeological Survey, PANDAS, scientists have mapped enormous faint arcs of stars encircling the galaxy. These structures are the remnants of smaller galaxies that Andromeda devoured long ago, their remains still tracing the paths they once followed before being absorbed. In fact, Andromeda's halo is so rich in these streams and substructures that it's often described as a kind of cosmic graveyard, each filament marking the final resting place of a once independent galaxy. The stars in this halo are typically old and metal-poor, meaning they formed early in the universe's history before later generations of stars enriched the cosmos with heavier elements. Many of them are ancient red dwarfs, stars nearing the end of their long lifespans, glowing faintly in shades of orange and red. These stars tell a story that stretches back more than 10 billion years, to a time when Andromeda itself was just beginning to take shape from the collapsing gas and dark matter that would one day form its majestic spiral arms.
What's striking about Andromeda's halo is not just its age, but its sheer size. Recent studies have revealed that the stellar halo extends out to at least 500,000 light-years from the galaxy's center, more than twice the diameter of the visible disk. Some faint halo stars have even been detected nearly 1,000,000 light-years away, suggesting that Andromeda's influence stretches far into what we might consider the space between galaxies. This means that the boundaries of Andromeda are anything but sharp. They fade gradually, blending into the intergalactic medium and eventually into the outskirts of the Milky Way's own halo. If we could see the stellar halo with the naked eye, if our vision were sensitive enough to detect such faint light, Andromeda would appear far larger in the sky than it does. Its glowing disk, which already spans several times the width of the moon in visible light, would seem enveloped by an enormous, faint mist of ancient stars stretching across a vast portion of the heavens. But even the most advanced telescopes struggle to capture this faint light. It's so diffuse that astronomers must use long exposures, specialized filters, and digital stacking techniques to reveal it, often taking hundreds of hours of observations to separate the halo's subtle glow from the background of the universe. The stellar halo doesn't just surround the galaxy, it connects it to its environment. Embedded within it are globular clusters, dense, spherical groups of ancient stars orbiting far from the main disk. Andromeda has over 450 known globular clusters, more than twice as many as the Milky Way. These clusters act like sentinels, tracing the gravitational field of the galaxy far into space. Some of them are thought to be remnants of the same small galaxies that were torn apart and assimilated, their central clusters surviving long after their parent systems were destroyed. By studying the composition and motion of halo stars, astronomers can reconstruct the assembly history of Andromeda, piecing together when and how it grew. The distribution of stars in the halo, their metallicities, chemical compositions, and their orbits reveal patterns consistent with multiple merger events over the past several billion years. Some of the stars in the outer halo likely originated in dwarf galaxies that merged with Andromeda as recently as 1 to 2 billion years ago, while others date back to the galaxy's earliest epochs. One of the most intriguing discoveries about Andromeda's halo came from the Hubble Space Telescope, which identified halo stars at incredible distances, nearly 1.3 million light-years from the galactic center. This means the halo could be even more extensive than previously believed, possibly overlapping with the Milky Way's halo in a vast, diffuse region of shared stars and dark matter. If so, the outer boundaries of the two galaxies are already beginning to blend together, forming a continuous gravitational landscape that unites them long before their visible disks ever touch. Andromeda's stellar halo reminds us that galaxies are not isolated islands of light. They are more like cosmic ecosystems, surrounded by layers of stars and debris that interact with the environment around them. The halo is the quiet, ancient remnant of all the violence and creation that built the galaxy, a record of every collision, every merger, every star that has drifted too far from the disk. It is the galaxy's memory, written across the faintest light of the night sky. And while the halo may seem empty compared to the brilliant core and spiral arms, it contains invaluable information about how galaxies evolve. In many ways, it's the most honest part of Andromeda. Stripped of the glamour of star-forming regions and the brightness of young suns, what remains is the bare scaffolding of the galaxy's history. But even this ghostly outer realm doesn't exist in solitude. Floating within and around Andromeda's halo are dozens of smaller, gravitationally bound companions, tiny galaxies caught in its powerful grasp. These satellite galaxies not only orbit Andromeda, but also help define the full extent of its influence in the local group, making the galaxy's domain even larger and more dynamic than its visible structure alone suggests. The grandeur of the Andromeda Galaxy extends far beyond its glowing disk and sprawling halo. Encircling it, like a retinue of celestial companions, are dozens of smaller satellite galaxies, faint, often irregular collections of stars that orbit their massive host like moons around a planet. These companions are an essential part of Andromeda's vast gravitational domain, offering a living demonstration of the galaxy's immense reach and influence across intergalactic space. To date, astronomers have identified more than 30 known satellite galaxies surrounding Andromeda, with new discoveries still being made through deep sky surveys. These smaller galaxies vary greatly in size, brightness, and composition. Some are relatively prominent dwarf ellipticals, while others are so faint that they were invisible until modern telescopes and sensitive imaging techniques revealed their diffuse glow. Together, they form a miniature ecosystem of galactic bodies orbiting within Andromeda's gravitational field, a microcosm of the broader universe's hierarchical structure.
The two most famous of Andromeda satellites are Messier 32, or M32, and Messier 110, or M110, both easily visible in long-exposure photographs of the main galaxy. M32 appears as a compact, bright oval just below Andromeda's disk, while M110 is a larger, more diffuse elliptical galaxy situated slightly above it. These two satellites are close enough to be gravitationally interacting with Andromeda, and both show signs of that relationship. M32, for instance, is a small elliptical galaxy with an unusually high density of stars near its core.
Astronomers believe this compactness may be the result of tidal stripping, a process in which Andromeda's immense gravity has pulled away much of M32's outer material, leaving behind only a dense, shrunken core. M110, on the other hand, still retains a more extended structure but bears the scars of past encounters as well. Its faint, diffuse halo shows subtle distortions and tidal streams, hints that it too has been shaped by Andromeda's powerful pull. These two satellites are close enough to be gravitationally interacting with Andromeda, and both show signs of that relationship. M32, for instance, is a small elliptical galaxy with an unusually high density of stars near its core. Astronomers believe this compactness may be the result of tidal stripping, a process in which Andromeda's immense gravity has pulled away much of M32's outer material, leaving behind only a dense, shrunken core. M110, on the other hand, still retains a more extended structure but bears the scars of past encounters as well. Its faint, diffuse halo shows subtle distortions and tidal streams, hints that it too has been shaped by Andromeda's powerful pull. Beyond these two well-known companions lies a host of fainter dwarf galaxies, many of them irregular in shape and barely luminous. Examples include Andromeda 1, 2, 3, and so on, a naming system that reflects the order in which they were discovered. These dwarf galaxies are mostly composed of ancient, metal-poor stars, suggesting they formed early in the universe's history and have undergone little star formation since. Some contain only a few million stars, a minuscule fraction compared to Andromeda's trillion-star population, yet their orbits and motions provide critical insight into the structure of the galaxy's dark matter halo. What's truly remarkable is the spatial arrangement of these satellites. Observations from the PANDAS, or Pan-Andromeda Archaeological Survey, have revealed that many of them are not randomly distributed, but appear to lie in a thin, rotating plane, a vast disk-like structure stretching across more than 1 million light-years. This plane of satellites has puzzled astronomers as it challenges standard models of how galaxies accrete and retain their companions. The existence of this coherent rotating system suggests that Andromeda satellites may share a common origin, perhaps remnants of a larger system that fragmented in the distant past. These satellites also play a crucial role in shaping Andromeda itself. As they orbit, Andromeda's gravity slowly pulls them apart, feeding streams of stars and gas into the main galaxy. Over billions of years, many small galaxies have already been absorbed, their stars now part of Andromeda's outer halo. The process continues even today. Faint stellar streams, remnants of long disrupted satellites, have been detected weaving through the space around Andromeda, silent testaments to its ongoing growth. The gravitational dance between Andromeda and its satellites is not a one-sided affair. While the massive host dominates the interaction, the collective gravitational pull of these smaller galaxies also exerts subtle influences on Andromeda's structure. They can warp its outer disk, trigger waves of star formation, and even cause the slight ripples observed in its spiral arms. These effects show that galaxies are not static objects, but living, evolving systems, constantly reshaped by their surroundings and companions. Many of these satellite galaxies are so dim that detecting them pushes modern astronomy to its limits. Using ultra-sensitive instruments such as the Subaru telescope, the Hubble Space Telescope, and more recently the James Webb Space Telescope, astronomers have begun to uncover even fainter companions, some with luminosities less than 100,000th that of the Milky Way. These ultra-faint dwarf galaxies are thought to be among the smallest and oldest galaxies in the universe, fossils from the early days of cosmic history that have survived billions of years under the protective shadow of Andromeda's massive halo. In many ways, Andromeda's system of satellites mirrors our own Milky Way's galactic family, which includes the large and small Magellanic Clouds and several faint dwarfs. Together, these twin systems, Andromeda and the Milky Way, form the core of the local group, a small cluster of galaxies bound together by gravity and surrounded by a few smaller members like the Triangulum Galaxy, or M33. Within this local cluster, Andromeda reigns as the dominant member, its gravitational field extending far enough to influence galaxies more than 1,000,000 light-years. If we could visualize Andromeda's gravitational influence, it would appear not as a simple sphere, but as a complex web of orbits, tidal streams, and dark matter contours. The satellites we see, glowing faintly in the shadows of their host, are just the brightest knots in that web. Each one tells a story of cosmic connection, a reminder that galaxies are not solitary wanderers, but part of vast gravitational families stretching across the fabric of space-time. These companions also hint at Andromeda's future. As the galaxy continues to move toward the Milky Way, some of its satellites will be swept along, becoming part of the enormous merger event that will one day unite both galactic systems. Others may be cast adrift, flung into the void as gravitational tides reshape everything in their path. The presence of these dozens of satellite galaxies illustrates not just Andromeda's size, but the true extent of its dominance. Its gravitational empire stretches across millions of light-years, influencing everything within its reach. And though most of these companions are small and faint, together they form a living border around the Great Spiral, a testament to its cosmic power and the vastness of its domain.
But despite the enormity of Andromeda's reach, when we look up from Earth, we see only a faint smudge, a ghost of light floating in the dark. To understand why, we must shift from the physical to the perceptual, to explore how something so colossal can appear so small in the night sky, and what that tells us about the vast distances that separate us from our nearest galactic neighbor. From our vantage point on Earth, the Andromeda Galaxy is both humbling and deceptive. It is the largest and most massive galaxy in our cosmic neighborhood, spanning over 220,000 light-years across. Yet, to the naked eye, it appears as little more than a faint, fuzzy smudge of light in the constellation of Andromeda. This tiny patch of brightness, barely perceptible without dark skies, conceals one of the grandest structures in the universe, a colossal spiral galaxy whose true scale defies imagination. The reason for this discrepancy between physical size and apparent size is simple: distance. Andromeda lies about 2.5 million light-years away from us, meaning its light, traveling at 300,000 kilometers per second, takes 2.5 million years to reach our eyes. That staggering distance causes even a galaxy of its immense scale to appear minuscule to our limited human perspective. The light we see from Andromeda tonight began its journey long before modern humans existed, before the first sparks of civilization ever flickered on Earth. Yet here's the remarkable part. Despite appearing so small and faint, Andromeda's apparent size in the sky is actually enormous. If our eyes were sensitive enough to detect its full, faint glow, Andromeda would stretch across an area of the sky roughly 6 times the width of the full moon. Its disk spans about 3 degrees from edge to edge, an astonishing visual breadth for something located millions of light-years away. It's not brightness that limits our view, but the faintness of the galaxy's outer regions, which are spread thinly across such a wide expanse that their light barely registers on the human eye. Under dark, rural skies, far from the glare of city lights, Andromeda can be spotted as a pale, elongated mist just above the horizon in the northern hemisphere during autumn and early winter. It sits nestled within the constellation Andromeda, near the star Mu Andromedae, and is best seen with averted vision, a technique where you look slightly to the side of an object rather than directly at it to detect faint light. Through binoculars or a small telescope, the galaxy's oval shape becomes clear, its bright central bulge shining like a hazy core surrounded by a soft, ghostly halo of starlight. When photographed through long exposures, however,
Andromeda transforms. What appears to the eye as a dim patch blossoms into a magnificent spiral, an island universe filled with billions of suns, laced with dark dust lanes and glowing blue star clusters. These photographs, taken by both amateur and professional astronomers, reveal the galaxy's sweeping arms in vivid detail, showcasing what our eyes cannot see, but our instruments can capture. To grasp the scale of Andromeda's appearance, consider this. If you could somehow see the galaxy in its full visible extent, it would cover a portion of the sky wide enough to stretch from one side of your outstretched hand to the other. Imagine looking up at night and seeing a vast, glowing spiral suspended across the heavens, a luminous neighbor hovering above, its light quietly mingling with the stars of our own Milky Way. That is the true size of Andromeda in our sky, hidden only by the limitations of human vision. The faintness of Andromeda's light also carries a profound implication. Every photon reaching Earth today represents a story of endurance, light that has traveled across the cosmic void for millions of years without interruption. The starlight that now strikes your retina left its source when early humans were still crafting tools from stone, when mammoths roamed the plains, and the continents were subtly shifting toward their modern forms. In a sense, when you look at Andromeda, you are seeing into the deep past, the galaxy as it was 2.5 million years ago. Even more striking is how Andromeda's light compares to that of the moon. The moon, though small in size, about 347,000 kilometers in diameter, is just 384,000 kilometers away. It appears large and bright because it is close. Andromeda, in contrast, is 600 trillion times further away, yet its light still reaches us strongly enough to be visible without any aid. That simple fact is awe-inspiring. It means the combined brilliance of its trillion stars is so immense that even from across intergalactic space, their collective glow pierces the darkness to touch our tiny world. For astronomers and skywatchers alike, observing Andromeda is a deeply humbling experience. It reminds us that the human eye, though small, though limited, can still perceive something so vast and ancient that it transcends our own existence. The faint patch we see is a bridge between two galaxies, a glimpse across the cosmic void that separates us from our nearest galactic neighbor. Interestingly, Andromeda's visibility has also played a historical role in astronomy. It was one of the first objects that challenged humanity's sense of scale. Early observers, seeing it with the naked eye, assumed it must be a nearby cloud within the Milky Way. It wasn't until telescopes and later spectroscopy revealed its true nature that the enormity of what we were looking at became clear. What we see as a mere blur of light is in truth an entire galaxy larger than our own, a collection of suns, planets, and nebulae too vast to comprehend. If the skies above our cities were as dark as they were in ancient times, Andromeda would likely be a familiar sight to everyone. Children could look up and spot the faint hazy glow of another galaxy without needing a telescope, realizing that our universe extends far beyond the Milky Way. It is a sobering thought that one of the grandest objects in the cosmos is still visible from Earth with nothing but human eyes. Yet most of us rarely see it because of the artificial light that floods our nights.
For those who venture to dark mountain ranges, deserts, or remote countryside, catching a glimpse of Andromeda feels almost spiritual. You stand beneath the stars, and there it is, a smudge of ancient light, faint but steady, whispering across millions of years of time. It's not just a galaxy you're seeing, it's a message from the universe, a reminder of how small we are and how vast the cosmos truly is. And though it may appear distant and serene, that faint glow carries a deeper story of motion and destiny. Because while Andromeda hangs quietly in our sky now, it is not still. It is moving toward us, closing the gap between our two galaxies at an astonishing pace, setting the stage for one of the most dramatic events in the history of the cosmos.
Though it glows softly and silently in the night sky, the Andromeda Galaxy is not a still, distant ornament of the cosmos. It is in motion, hurtling through the darkness of intragalactic space on a collision course with our own Milky Way. The two great spirals, separated by roughly 2.5 million light-years, are slowly but inexorably being drawn together by their mutual gravity. Andromeda is moving toward us at a velocity of about 110 kilometers per second. That's roughly 250,000 miles per hour. An extraordinary speed by human standards, but in cosmic terms, it's a gentle, inevitable drift across the vastness of space. At that speed, Andromeda closes the distance between our galaxies by about 1 light-year every 9,000 years. Though the gap remains immense, this slow gravitational pull ensures that one day, billions of years from now, our galaxies will meet in a titanic cosmic merger. The collision won't happen anytime soon in human terms, but on the scale of the universe, it's already in motion. In about 4 to 5 billion years, Andromeda and the Milky Way will begin to collide, their spiral arms stretching and warping as they intertwine to form a new, larger galaxy. The knowledge that Andromeda is heading toward us comes from precise astronomical measurements, particularly spectroscopy, the study of how light shifts in wavelength as objects move. When an object in space moves away from us, its light stretches, shifting toward the red end of the spectrum, a phenomenon known as redshift. Conversely, when it moves toward us, it compresses, shifting toward the blue end, a blue shift. Andromeda is one of the few large galaxies in the universe that shows a noticeable blue shift. Most galaxies are receding from us because of the universe's overall expansion. But Andromeda is so close and its gravitational bond with the Milky Way so strong that their mutual attraction overcomes the general expansion of space. This motion has been known for nearly a century. In 1912, astronomer Vesto Melvin Slipher was the first to measure the Doppler shift of Andromeda's light and discovered that it was moving toward Earth. His finding was revolutionary. It was one of the first pieces of evidence that galaxies could have significant motions relative to one another. Decades later, more precise measurements confirmed that Andromeda's approach speed was around 110 kilometers per second, and that the two galaxies were gravitationally bound in the same local system. But Andromeda's movement isn't just a straight line plunge toward us. Like two dancers in a slow waltz, the Milky Way and Andromeda are influenced not only by their mutual gravity, but also by their sideways motion, the smaller lateral component of their velocity across the sky. For a long time, astronomers weren't sure whether Andromeda might miss us entirely, perhaps just brushing by and continuing on its way. However, with the help of data from the Hubble Space Telescope and more recently the Gaia spacecraft, scientists have determined that Andromeda's sideways motion is relatively small. This means the galaxies are not just glancing past each other, they are on a direct course for collision. It's an almost paradoxical truth. Something so serene to the eye is in fact rushing headlong toward one of the most dramatic encounters in cosmic history. The galaxies are moving together through a region of space largely empty of matter, their enormous dark matter halos already beginning to interact. The dark matter acts like an invisible bridge, pulling the galaxies closer even as their visible structures remain millions of light years apart. When Andromeda finally reaches the Milky Way, the event won't resemble a catastrophic explosion, but rather a slow, majestic merger unfolding over hundreds of millions of years. Despite both galaxies containing hundreds of billions of stars, the vast distances between those stars mean that direct collisions between individual suns are incredibly unlikely. Instead, the two galaxies will pass through each other, their shapes distorting by gravity, their spiral arms flung into long tidal tails of stars and gas. Computer simulations, particularly those run by NASA's Goddard Science Center, have given us a glimpse of this future. The first encounter will likely occur in about 4 billion years, when Andromeda's disk begins to overlap with the Milky Way's.
The galaxies will pass through each other, stretching into elongated forms before gravity pulls them back together for a second, slower collision. Over time, their gas and dust will condense, sparking new waves of star formation while their supermassive black holes spiral inward toward a violent union at the core of the merged system. Eventually, after about 6 billion years, the two galaxies will settle into a new shape, an enormous elliptical galaxy sometimes nicknamed Milkomeda or Milkodromeda. This new galaxy will be vastly larger than either of its predecessors, containing trillions of stars and a combined dark matter halo spanning millions of light years. The night sky from Earth's location, or whatever remains of our solar system, would look dramatically different. Instead of the familiar band of the Milky Way, future observers would see great arcs of stars filling the heavens, Andromeda's bright core merging with our own in a breathtaking celestial spectacle. Ironically, the Sun itself, by then a fading red giant near the end of its life, would witness the beginnings of this galactic ballet. The Earth may no longer be habitable, but our solar system, drifting within one of the Milky Way spiral arms, will be swept into the gravitational tides of the approaching Andromeda. As the two galaxies merge, our star may find itself cast into a new orbit, flung into the outskirts of the forming Milkomeda, or perhaps drawn inward toward the bright new center. In this sense, Andromeda's approach isn't the threat so much as a promise of transformation. The collision will reshape both galaxies, redistributing their stars, reigniting their stellar nurseries, and giving birth to an entirely new cosmic structure. It's the universe's way of recycling itself, creation through destruction, beauty born from chaos. Andromeda's approach reminds us of a profound truth about the cosmos. Everything is in motion. Even what seems still, the stars in our night sky, the galaxies in the distance, is constantly changing, orbiting, and colliding on timescales far beyond our comprehension. The quiet smudge of light we see above us tonight is not just a neighboring galaxy, but our future partner in an immense cosmic dance. And as we imagine that slow-motion collision unfolding billions of years from now, it leads us naturally into the next stage of Andromeda's story, the future Milky Way-Andromeda merger, when these two spirals will cease to exist as separate entities and become something altogether new. A vast merged galaxy shining at the heart of a transformed local group.
The approaching collision between the Milky Way and the Andromeda Galaxy is one of the most spectacular and inevitable events in the future of our cosmic neighborhood. Though it will not occur for roughly 4 billion years, astronomers already have a remarkably detailed idea of how it will unfold, thanks to decades of observation, precise measurement, and advanced computer simulations. What's to come is not a destructive crash, but a grand merger, a slow, gravitationally choreographed transformation that will reshape both galaxies into something entirely new, a massive elliptical galaxy that astronomers have fittingly dubbed Milkomeda, or sometimes Milkodromeda. To grasp the scale of this future event, it helps to remember just how enormous both galaxies are. The Milky Way spans about 100,000 to 120,000 light-years across, while Andromeda's luminous disk stretches to about 220,000 light-years. Each contains hundreds of billions of stars, vast clouds of gas and dust, and immense dark matter halos that extend for millions of light-years in every direction. These halos are already beginning to overlap, forming an invisible bridge of gravity between the two galaxies. That gravitational attraction is what's drawing them together, slowly closing the 2.5 million light-year gap that separates us. When the collision begins, it won't happen all at once. From our perspective, if any human or descendant of humanity could still witness it, Andromeda would gradually grow larger and brighter in the night sky over millions of years. Its spiral arms would become distinct to the naked eye, filling much of the heavens as it approached. Eventually, its disk would dominate the sky, glowing like an immense celestial storm until the first close pass occurs. That first encounter will likely take place in about 4 billion years according to simulations run by NASA's Goddard Space Flight Center and the Harvard-Smithsonian Center for Astrophysics.
During this initial pass, the galaxy's outer regions will begin to interact. Their shapes will warp under the force of mutual gravity, and long tidal tails, streams of stars, dust, and gas, will stretch across millions of light years, thrown outward like ribbons of starlight. These tidal forces will distort the spiral arms of both galaxies, creating spectacular arcs and loops visible across intergalactic space. Despite the violent appearance of this event, it's important to remember that space within galaxies is mostly empty. The stars themselves will almost never collide directly. The average distance between stars and the Milky Way is several light years, comparable to grains of sand separated by kilometers. So when the galaxies pass through one another, their stars will glide by with hardly a chance of collision. What will happen instead is a vast reorganization. Gravitational forces will alter the orbits of billions of stars, flinging some into new paths, drawing others toward the combined center, and creating new waves of star formation as gas clouds are compressed and shocked by the interaction. As the galaxies continue to pull on one another, they will slow down, reverse direction, and fall together again. This second encounter, perhaps a few 100 million years later, will mark the beginning of the true merger. The spiral arms will begin to dissolve, their orderly patterns disrupted by the gravitational chaos. The disks will overlap completely, and the two supermassive black holes at their centers, one about 4 million solar masses in the Milky Way and another around 100 million solar masses in Andromeda, will spiral toward each other in a slow, inevitable dance. Over hundreds of millions of years, they will lose energy through gravitational radiation until they finally coalesce, releasing a burst of gravitational waves powerful enough to ripple across the entire universe. By the time the merger settles, roughly 6 to 7 billion years from now, the Milky Way and Andromeda will no longer exist as separate spiral galaxies. Instead, they will have combined into a single enormous elliptical galaxy. Unlike the elegant flat spirals we see today, this new galaxy will be more rounded and diffuse, with no distinct arms or flattened disk. Its stars will move in random orbits rather than neat rotations, and its overall structure will resemble the giant elliptical galaxies we observe in distant clusters. Astronomers estimate that Milkomeda will stretch across perhaps 500,000 light-years, twice the size of Andromeda's current disk, and will contain more than 1 trillion stars. The merger will also spark a renaissance of star formation. When the gas clouds from both galaxies collide and compress, they'll ignite bursts of stellar creation, lighting up the new galaxy with clusters of young, hot, blue stars. However, this phase will be temporary. Once the available gas is consumed or dispersed, star formation will gradually decline, and Milkomeda will evolve into a calmer, redder galaxy, filled mostly with aging stars. In time, it will become a massive, quiescent elliptical, a majestic but quieter descendant of the two great spirals that birthed it. From the perspective of the solar system, the event will be both extraordinary and survivable. By the time the merger occurs, the Sun will be nearing the end of its life. About 5 billion years from now, it's expected to expand into a red giant, engulfing Mercury and Venus, possibly Earth as well. If any remnants of our solar system remain, they'll find themselves adrift within the new Milkomeda, perhaps orbiting far from the galactic center or flung into intergalactic space. For any observers in that far future, the night sky would be awe-inspiring beyond description, filled with countless new stars and vast arcs of glowing gas as two galaxies merge and evolve before their eyes. Milkomeda's formation will mark not an end, but a cosmic transformation. It's part of the natural life cycle of galaxies, a process repeated countless times across the universe. We see it in distant galaxies captured by the Hubble Space Telescope, their shapes distorted by mergers in progress. What will happen to us is not unique. It's the destiny of most large galaxies, as gravity slowly draws them together into ever larger systems. Eventually, even Milkomeda's story will continue. In perhaps tens of billions of years, the merged galaxy will drift closer to its smaller companion, the Triangulum Galaxy, M33, possibly absorbing it as well. over unimaginable timescales. As the universe expands and cools, Milkomeda will stand alone in the darkness, a vast, elliptical island of ancient stars, shining quietly in a night sky emptied of other galaxies. What began as a faint smudge in our sky, a distant spiral visible to the naked eye, will in time become our own cosmic home. The Milky Way and Andromeda, once separate entities, will merge into a single luminous structure that represents both the end of one chapter and the beginning of another in the ever-evolving universe. But beyond the spectacle of this future merger lies a deeper truth about scale and space, because even though galaxies are incomprehensibly vast, they are also mostly empty. Their collision, while grand on a galactic scale, will be almost serene at the level of individual stars. This contrast between immensity and emptiness reveals one of the most profound lessons about the nature of the cosmos itself. The coming Milky Way-Andromeda merger is not only a vision of cosmic grandeur, it is also a profound lesson in scale. It reminds us that even when two of the largest spiral galaxies in our cosmic neighborhood collide, the universe remains an ocean of vast emptiness. The distances between stars are so immense that despite the galaxy's trillion suns, almost no stars will physically collide. This fact is both humbling and awe-inspiring, revealing that the true nature of the cosmos is one of unimaginable size, silence, and spaciousness.
When Andromeda and the Milky Way finally meet, their disks will interpenetrate like two ghostly spirals of light. To the naked eye, it might look as though they're smashing together, a storm of starlight and gravity. Yet, if you could zoom in, if you could follow one single star as the collision unfolded, you'd see almost nothing around it. The nearest neighboring star would remain light years away, trillions of kilometers of empty space separating them. The galaxy's glowing arms would swirl and twist, their stars drawn into new orbits. But actual contact between stellar surfaces would be exceedingly rare, perhaps never happening at all. To understand why, it helps to imagine the galaxy on a smaller, human scale. If each star in Andromeda were the size of a grain of sand, the next nearest grain would be several kilometers away. Even though there are hundreds of billions of stars, the sheer distances between them make galaxies more like vast, diffused clouds than solid structures. When two such clouds merge, their individual particles, their stars, simply flow around one another, pulled this way and that by gravity, but rarely touching. This is the paradox of cosmic immensity. Galaxies are among the largest objects in the universe, yet they're composed mostly of nothing. Between stars lies the great dark sea of interstellar space, filled only by a whisper of gas and dust so thin that, on average, you would have to travel trillions of kilometers to encounter a single atom. Even Andromeda's dense core, glowing brightly in telescopic images, is far emptier than the best vacuum humans can create in the laboratory. So, when these two colossal galaxies begin their union, what actually collides is not the stars themselves, but their gravitational fields. As they pass through one another, their gravity will warp space like waves rippling through water. Whole clusters of stars will be deflected into new trajectories. Some will be flung into intergalactic space, while others will be pulled inward toward the growing center of the new galaxy. The interaction will reshape their orbits, trading the tidy rotation of spirals for the more chaotic motion of stars in an elliptical galaxy. Meanwhile, the interstellar gas and dust, the raw material for stars, will behave differently. Unlike the stars, these clouds can collide and compress. When they do, they will trigger bursts of star formation, lighting up the new galaxy in brilliant blue-white clusters of newborn suns. For a few hundred million years, Milkomeda will blaze with new light, its skies rich with stellar nurseries. But when the gas is spent, the star birth will subside, and the merged galaxy will settle into quiet stability, its stars drifting peacefully through the vast emptiness once again. This serene outcome, despite the enormity of the event, underscores one of the most profound truths in all of astronomy.
The universe is spacious beyond comprehension. Even when galaxies collide, most of what happens is the slow dance of gravity, not the violent clash of matter. The cosmos is built on vast distances and deep stillness, or even the grandest events unfold over timescales so long that entire species, civilizations, and planets could rise and fall between their first act and their last. In this way, the Milky Way-Andromeda merger is both a spectacle and a metaphor. It's a reminder that size in the universe is relative, that our intuitions about closeness and collision fail completely at galactic scales. What seems like contact from a distance is in reality motion through emptiness, governed by forces so gentle and slow that they defy our everyday understanding of interaction. For the stars themselves, the merger will hardly be noticed. A sun like ours, orbiting calmly in its galactic arm, will simply feel its path curve over billions of years, responding to the new gravitational landscape. If our solar system survives, it may find itself flung to the outskirts of Milkomeda or drawn toward the dense core where two supermassive black holes merge in the galaxy's heart. From that distant vantage point, the night sky would look utterly transformed. Instead of the familiar band of the Milky Way, the heavens would shimmer with vast curtains of starlight, the mixed remnants of both galaxies stretched across the sky. The thought of such an event, colossal, inevitable, and yet almost peaceful, reveals how different cosmic reality is from human perception. To us, collisions mean destruction, but in the cosmos, they often mean creation and transformation. Galaxies grow by merging, they are sculpted by encounters. The universe builds its grandest structures not through violent chaos, but through the slow, delicate weaving of gravity acting across unimaginable distances. Andromeda's approach and eventual merger with the Milky Way illustrate this balance perfectly. It's both cataclysm and calm, violence and grace, a reminder that even the most awe-inspiring transformations in the universe can occur in near silence. On the human scale, it's beyond imagining. On the cosmic scale, it's just another step in the endless evolution of galaxies. So, while the idea of our galaxy colliding with another might sound apocalyptic, it's actually part of a natural cosmic rhythm that has been unfolding since the dawn of time. Galaxies have merged countless times before, and they will continue to do so long after Milkomeda itself has faded. And in this perspective, our future collision is not an ending, but a continuation, a renewal of form, a new chapter in the endless life cycle of the cosmos.
And yet, when we ponder this event, when we imagine entire galaxies passing through each other like shimmering ghosts, we can't help but confront the limits of our own understanding of scale. How can the mind truly grasp distances measured in millions of light years, or events unfolding over billions of years? To make sense of it, we must bring it down to the human scale, to compare the vastness of Andromeda and the Milky Way with distances and sizes that we can just barely comprehend. When we talk about Andromeda's vastness, a galaxy more than 220,000 light-years across and 2.5 million light-years away, the numbers themselves almost lose meaning. They're so large, so detached from anything we experience in everyday life, that they seem abstract, like statistics written in light rather than reality. To truly appreciate what those numbers mean, we have to step back and look at them through the lens of human scale, to translate the incomprehensible immensity of the universe into something that our minds can begin to grasp. Start with a single light year, the distance light travels in 1 year. Light, the fastest thing in existence, moves at about 300,000 kilometers per second, or roughly 186,000 miles per second. In 1 second, it could circle the Earth nearly 7.5 times. In 1 year, it covers about 9.46 trillion kilometers, or 5.88 trillion miles. That's just 1 light year. Now, imagine a distance of 2.5 million light years, the gulf separating us from the Andromeda Galaxy. That's 23 quintillion kilometers, or 23 followed by 18 zeros. If you could somehow travel at the speed of light, a feat far beyond our current technology. It would still take you 2.5 million years to get there. For perspective, 2.5 million years ago, early humans were just beginning to use stone tools. Civilization, art, language, even our species did not yet exist. The light we see from Andromeda tonight began its journey then, crossing the void through ages of planetary and biological evolution to finally meet our eyes here, now. Even our fastest spacecraft barely scratched that distance. The Voyager 1 probe, launched in 1977 and now traveling through interstellar space, is moving at about 17 kilometers per second, nearly 60,000 kilometers an hour. At that speed, it would take Voyager more than 40 billion years to reach Andromeda, almost 3 times the age of the universe itself. To bring this into something visual, imagine shrinking the Milky Way down to the size of a dinner plate, about 30 centimeters or 12 inches across. On that same scale, Andromeda would be another plate about twice as wide, roughly 60 centimeters, 2 feet across, sitting 6 meters away. That's the empty space that separates them. Not much when viewed on that scale. But now imagine each millimeter on those plates representing hundreds of trillions of kilometers, and you start to sense how incomprehensibly stretched our universe really is. Even the stars within a single galaxy are separated by staggering distances. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away, nearly 40 trillion kilometers. If the Sun were the size of a tennis ball, Proxima Centauri would be another tennis ball placed 1,000 kilometers away. That's how lonely even neighboring stars are. So when we talk about Andromeda's trillion stars, all orbiting within a disk 220,000 light-years wide, we're talking about a city of suns so vast that each building is separated by gaps larger than the space between entire solar systems. Let's scale up again. Suppose you could somehow drive to Andromeda in a car traveling at 100 kilometers an hour, about 60 miles per hour. If you never stopped, not even for a moment, it would take you roughly 26 trillion years to arrive, about 2,000 times longer than the age of the universe. Even at the speed of the fastest jet aircraft ever built, around 3,500 kilometers per hour, the journey would take 750 billion years. These numbers don't just stretch the imagination, they break it. They force us to confront the reality that the cosmos operates on scales utterly beyond our capacity to experience directly. Even within Andromeda itself, the distances are awe-inspiring. A beam of light traveling from one edge of the galaxy to the other would take 220,000 years to complete the trip. That means if a civilization lived on one planet on one side of Andromeda and sent a message made of light to another on the opposite side, the message would arrive long after entire human civilizations could have risen and fallen. And yet, despite its immensity, Andromeda still exists in what astronomers call our local group, a small cluster of galaxies. Beyond that lies the Virgo supercluster, spanning over 100 million light-years, and beyond that still, the Laniakea supercluster, a structure of galaxies so vast it takes light 500 million years to cross it. And beyond even that, the web of the observable universe, stretching 93 billion light-years in diameter, containing at least 2 trillion galaxies, each with billions of stars like Andromeda and the Milky Way. When viewed on this cosmic stage, even our majestic neighbor becomes just one faint brushstroke in an almost infinite tapestry. The mind struggles to hold these scales in focus. Our entire world, the oceans, mountains, and clouds we call home, is merely a speck of dust in this vastness. The Earth's diameter is only about 12,742 kilometers. The Sun, by comparison, is so large that 1.3 million Earths could fit inside it. And yet the Sun itself is just one of the hundreds of billions of stars that form the Milky Way, which in turn is dwarfed by Andromeda's mass and breadth.
It's easy to feel insignificant in the face of such enormity, but the wonder of astronomy isn't in making us feel small, it's in revealing how extraordinary it is that we can understand this scale at all. From a small blue planet orbiting an ordinary star, life has emerged with the capacity to measure, to imagine, and to comprehend the distances between galaxies millions of light years apart. The fact that human minds, tiny sparks of consciousness, can conceive of Andromeda's size is a triumph of curiosity, not a testament to our smallness, but to our ability to grasp infinity. If you could stand on a planet within Andromeda and look back toward the Milky Way, you'd see our galaxy as a faint, glowing spiral, a small smudge of light hanging in the darkness, much as we see Andromeda from Earth. In that simple symmetry lies a beautiful truth. Across the immense gulf of space, two galaxies face one another like distant reflections, each containing countless stars, planets, and perhaps even other beings who look up and wonder the same thing we do. How vast is it all? And what is our place within it? This human perspective, the attempt to scale the infinite, is what gives astronomy its poetry. It reminds us that while we are minuscule compared to Andromeda, we are also a part of the same cosmic story. The light from our sun, like the light from its trillion stars, flows through the same universe, and in understanding the scale of that universe, we find meaning in our smallness, not insignificance, but connection. And that sense of connection leads naturally to a final reflection: why studying Andromeda matters at all. For beyond its beauty and scale, Andromeda is also a key to understanding our own galaxy, our cosmic origins, and the evolution of everything we see when we look up at the night sky. Studying the Andromeda Galaxy isn't just about gazing in wonder at a distant object, it's about looking into a mirror that reflects our own cosmic story. Andromeda is not merely our nearest galactic neighbor, it is also our closest analog, a system so similar to the Milky Way that to study it is, in many ways, to study ourselves. Its proximity, scale, and detail make it one of the most important laboratories in all of astronomy, a natural observatory for understanding how galaxies form, evolve, and interact in the vast framework of the universe. When astronomers examine Andromeda's structure, its spiral arms, central bulge, and halo, they are in essence seeing the Milky Way from the outside. Because we live inside our own galaxy, we can never truly observe its full shape directly. We can only infer it from the distribution and movement of stars around us. Andromeda, being close enough to resolve in extraordinary detail, yet distant enough to view as a whole, offers a rare opportunity to study a spiral galaxy similar to our own in its entirety. It's like stepping outside your house for the first time and seeing how it actually looks from the street. By mapping Andromeda's stars, gas, and dust, astronomers can test theories about how galaxies like the Milky Way are structured. For instance, observing the motion of Andromeda's stars allows scientists to refine models of galactic rotation and dark matter distribution. The discovery that Andromeda's outer stars orbit faster than expected was one of the earliest and strongest pieces of evidence for the existence of dark matter, that mysterious, invisible substance that makes up most of the universe's mass. Through Andromeda, we gained one of the first glimpses into the hidden architecture of the cosmos. Its sheer size and diversity also help astronomers understand the life cycles of galaxies. Within its enormous disk, Andromeda hosts regions of active star formation alongside older, quieter zones filled with ancient stars. This mix allows scientists to observe every stage of galactic evolution in one place: the birth of stars from interstellar clouds, their long lifetimes orbiting the galactic core, and their eventual deaths as supernovae that seed new generations of stars with heavy elements. By studying how these processes differ between Andromeda's arms, bulge, and halo, astronomers can trace the timeline of how galaxies like ours grow and change over billions of years. Andromeda's satellite galaxies and stellar halo are equally revealing. The faint streams of stars surrounding it, remnants of smaller galaxies that were torn apart, provide direct evidence of how large galaxies assemble their mass. The Milky Way is undergoing the same process right now, slowly absorbing dwarf galaxies such as Sagittarius and Canis Major. By watching Andromeda's interactions from afar, scientists can witness the same events that are shaping our own galaxy, but with the clarity of an outside observer. Each star stream, each dwarf companion tells part of the story of cosmic construction, how galaxies cannibalize their neighbors to become the giants we see today. Even Andromeda's differences from the Milky Way teach us something. Its larger size, more massive core, and denser star population allow astronomers to explore how small variations in mass and structure lead to vastly different fates. Why, for instance, does Andromeda have more globular clusters than the Milky Way? Why is its halo richer in substructures?
These questions aren't just about Andromeda, they're about the fundamental mechanisms that govern the formation of every galaxy in the universe. Studying Andromeda also provides insight into the future. Because it's moving toward us, we can observe its motion and simulate its eventual collision with the Milky Way. This helps astronomers understand what happens when galaxies merge, how their shapes change, how their black holes interact, and how new galaxies are born from the remnants of old ones. The detailed modeling of the Milky Way-Andromeda collision doesn't just predict our own fate, but it also explains the many elliptical galaxies we see throughout the universe, the end products of ancient mergers just like ours will be. Beyond its astrophysical importance, Andromeda is a bridge between the known and the unimaginable. Its light, reaching us after traveling millions of years through space, carries encoded information about the history of the universe. By analyzing that light, its color, composition, and energy, astronomers can trace how the elements forged in stars have enriched galaxies over time. In the glow of Andromeda is the story of stellar alchemy. Hydrogen and helium born in the Big Bang transformed over billions of years into carbon, oxygen, iron, and all the elements that make up planets, oceans, and life itself.
Andromeda also reminds us of our place in the cosmic order. Its closeness allows astronomers to calibrate their methods for measuring distances to other galaxies. Cepheid variable stars in Andromeda helped Edwin Hubble prove that it lay outside the Milky Way, a discovery that revealed for the first time that the universe was far larger than anyone had imagined. Today, those same types of stars and other standard candles in Andromeda continue to refine our cosmic distance scale, anchoring our understanding of how far away everything else in the universe truly is. Moreover, by comparing Andromeda with countless other galaxies observed by telescopes like Hubble, Gaia, and the James Webb Space Telescope, astronomers can see where our local group fits into the grander cosmic web. They can test whether galaxies like the Milky Way and Andromeda are typical or exceptional, helping to piece together the broader pattern of galaxy formation and cosmic evolution. Every detail we uncover about Andromeda, from the orbits of its stars to the faint wisps of its halo, contributes a vital clue to this universal puzzle. But perhaps the most profound reason Andromeda matters is philosophical. It stands as a tangible link between human curiosity and the infinite. When we look at Andromeda, we see the nearest great island of stars, a destination our descendants might one day reach. But we also see a reflection of ourselves, of our galaxy, our origins, and our destiny. The same physical laws that govern Andromeda shape our world, our sun, and the atoms in our bodies. The study of that distant galaxy is, in a very real sense, a study of our own cosmic identity. The faint smudge of light we glimpse in the constellation of Andromeda is more than a beautiful sight. It's a doorway into understanding how everything in the universe came to be. By exploring its size and structure, astronomers are not just cataloging a neighbor in the night sky. They are decoding the grand story of creation itself. And as our understanding deepens, we come full circle to the question that began this journey. How big is the Andromeda Galaxy? For in answering that, we discover that size is not only about distance or mass, it's about perspective, about the way we measure our own existence against the backdrop of eternity. So after all of this exploration, after tracing its spiral arms, weighing its trillion suns, charting its halo of dark matter, and imagining its future collision with our own, we return to the question that began it all. How big is the Andromeda Galaxy? The answer, in its simplest form, is that Andromeda is enormous, a colossal spiral of stars stretching 220,000 light-years from end to end, making it roughly twice the size of the Milky Way. It contains over 1 trillion stars, vast clouds of interstellar gas and dust, hundreds of globular clusters, and dozens of smaller satellite galaxies orbiting in its gravitational grip. Its invisible dark matter halo likely extends more than 2 million light-years, intertwining at the edges with the halo of our own galaxy.
Measured in sheer physical scale, it is one of the largest structures visible to the naked eye. A cosmic metropolis on a scale so vast that our entire solar system would be utterly lost within it, less than a mote of dust adrift among its radiant billions of suns. But the true size of Andromeda cannot be captured by numbers alone. It is vast not just in distance or dimension, but in meaning, in what it reveals about the universe and about ourselves. To study Andromeda is to stretch the human mind to its limit, to try and hold in our imagination something so immense that even light, the fastest thing in the cosmos, takes 2.5 million years to bridge the gap between its stars and our eyes. When you look at Andromeda on a dark night, you are seeing ancient light. Photons that began their journey before there were cities, before there were humans, before the very landscape of Earth took its modern form. You are looking not across space, but across time itself. Andromeda is also a reminder of connection. Though it may seem distant and unreachable, it's bound to us by gravity, drawn toward the Milky Way in a slow, silent embrace that will, billions of years from now, merge the two into one galaxy. Every moment that immense galaxy moves closer, closing the cosmic gap between us at more than 100 kilometers per second. In the distant future, its brilliant core will blaze in our night sky, and the two galaxies will combine their stars into a single greater whole, a new galaxy that will carry both legacies into eternity.
It's humbling to think that our own home galaxy, the Milky Way, and our grand neighbor, Andromeda, are just two among trillions of galaxies scattered across the universe. Each one is a city of stars, a cosmic island filled with worlds, clouds, and mysteries of its own. And yet from here, from this small blue planet orbiting an ordinary star, we have learned to measure them, to map them, and to understand them. We have learned that Andromeda is not just a smudge in the sky, but an entire universe in itself, one that mirrors our own and hints at our shared cosmic destiny. So, how big is the Andromeda Galaxy? It's too big for words to contain, too vast for the mind to truly comprehend. It is hundreds of thousands of light years wide, its mass measured in trillions of suns, its reach stretching across intergalactic space. And yet, in the grand design of the cosmos, it is only one galaxy among countless others, one shining spiral adrift in an endless sea of light. Perhaps the better question isn't how big is Andromeda, but rather, how extraordinary is it that we can even ask? That human eyes can look up at the night sky and glimpse its faint, ancient glow. That human minds can measure, model, and imagine something so distant, so immense, and so beautiful. And that act of seeing, we bridge the gulf between ourselves and the infinite. Andromeda's light, falling softly on our world after millions of years of travel, reminds us of who we are, a species that looks outward, that hungers to understand, that dares to measure the immeasurable. Its enormity humbles us, but its presence inspires us. It tells us that no matter how small we may seem, we are part of something vast and connected, part of a living universe whose scale is beyond imagining, yet whose beauty is within our reach. The Andromeda Galaxy, a trillion stars, hundreds of thousands of light years across, 2.5 million light years away, is vast beyond imagination. And yet, it is just one galaxy among countless others, one shining fragment of a universe that stretches endlessly in every direction. Its light is a message from the cosmos itself, that we are tiny, yes, but also luminous, threads of consciousness woven into the same fabric of starlight that spans the heavens. And so, when you next stand beneath the dark sky and glimpse that faint, misty oval just above the horizon, know that you are not merely looking at another galaxy. You are looking across time and space, across billions of years of cosmic history, into a realm of unimaginable scale and silent majesty.
That faint shimmer of light is a testament to the immensity of creation and to the miracle that we are here, capable of seeing it, wondering at it, and calling it by name: Andromeda. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.